Hi all, welcome to another interesting video of linear control system, that is transfer function of armature controlled DC motor. That is, in the previous subjects we have learned armature controlled DC motor and field controlled DC motor like that. Okay, so this is a figure of an armature controlled DC motor. So here you can see this is the field and this is the armature part. So for an armature controlled DC motor, the field supply is fixed. Okay, that is, the field is supplied from a constant source, but the armature is supplied from a variable source. That is, the armature voltage is varying here. That is for mainly the speed of the DC motor. Okay, the speed of the DC motor here is directly proportional to the armature voltage and inversely proportional to the flux in field winding. So in armature controlled DC motor, the desired speed is obtained by varying the armature voltage. Okay, and the speed control system is an electromechanical control system here, and the mechanical system consists of the rotating part of the motor and the load connected to the shaft of the motor. Okay, and these are some parameters we are using in this derivation. That is, first one is Ra, that is armature resistance; La, armature inductance; Ia, armature current; Va, armature voltage; Eb, back EMF; Kt, torque constant; T, torque developed by the motor; theta, angular displacement of shaft; J, moment of inertia of motor and load; B, frictional coefficient of motor and load; and last Kb, that is back EMF constant. Okay, and we are going to analyze this circuit, how we can write the mathematical equations governing this simple DC motor. Okay, so the first equation is based on the Kirchhoff's voltage law of the entire circuit. So this is the equivalent circuit of the armature shown. That is, this is the armature resistance Ra, and this is the armature inductance La, and this is the back EMF developed, and Va is the applied voltage. Okay, so by Kirchhoff's Kirchhoff's voltage law, we can write Ia into Ra plus La into dIA by dt plus Eb is equal to applied voltage Va. Okay, so this is the first equation, and also the next one is the torque equation of the motor. And for a DC motor, we know that the torque is directly proportional to flux and armature current. So here we are considering an armature controlled DC motor. So for that case, the field is fixed. Okay, that is, the field is supplied from a constant source, so hence the flux will be fixed. Okay, so here we have to consider only the current part, that is armature current. So torque is directly proportional to armature current, and we obtain T is equal to Kt into A, where Kt is the torque constant. So this is the second equation. And next one, we are considering the motor as a mechanical rotational system. Okay, that is it is a rotational body. So for a rotational system, we know that the mechanical rotation system can be represented by three elements, that is the mass and the dashpot and spring. That is, the mass is represented by its moment of inertia, that is weight, and dashpot is the representation for the friction, and the spring is the representation for the elastic deformation. So here for our DC motor, J, that is the moment of inertia, that is mass element is there and the dashpot is there, but here we can't see the spring, that is the elastic deformation, because for the electrical machines we are considering the effect of elastic deformation as very less. We are neglecting that element. So here you can see only two elements, that is the moment of inertia, that is mass, and dashpot B, and we are applying a torque T here in this direction. Okay, and theta is the angular displacement. So from this figure we obtained an equation. Okay, that is the torque balance equation, as the applied torque T is equal to opposing forces. So T is equal to opposing force are J into d square theta by dt square plus next one is B into d theta by dt. Okay, that is the opposing force due to mass is J into d square theta by dt square, and opposing torque due to the dashpot is B into d theta by dt. So J into d square theta by dt square plus B into d theta by dt is equal to T. So this is the third equation. So first, second and third. And one more equation is there, that is based on the back EMF of DC machine, and we know that the back EMF is directly proportional to the angular velocity. Okay, that is EB directly proportional to d theta by dt, or we can write it as EB is equal to KB into d theta by dt, and where KB is the back EMF constant, and this acts as the fourth equation. So in effect we can write all these four equation like this, that is IA into RA plus L into dA by dt plus EB is equal to VA first one, T is equal to KT into A second one, J into d square theta by dt square plus B into d theta by dt is equal to T third one, EB is equal to KB into d theta by dt. And we are going to take the Laplace transform of all these four equations, and we obtain as the Laplace transform of the first one is IA of S into RA plus LA into dA by dt is here. So the second term becomes LA into S into IA of S. And here also we are considering all the equations with zero initial conditions. Okay, Laplace transform of all the equations with zero initial conditions. So we have to take the first part only, that is LA into S into IA of S plus EB of S plus is equal to VA of S. First equation is converted into Laplace transform. And second one is T is equal to KT into A, so T of S equal to KT into A of S. Third one is J into S square theta of S plus B into S into theta of S is equal to T of S. Fourth one is EB of S equal to KB into S into theta of S. Okay, so here we can see in the four equations the second and third one is regarding the torque. Okay, that is T of S. So we are going to equating these 1.17 and 1.18 equations. So by equating these two one, we obtain that is KT into A of S is equal to J into S square theta of S plus B into S into theta of S. Okay, so by rearranging that we obtain IA of S, that is armature current, as IA of S equal to J into S square plus BS by KT into theta of S. Okay, and here the 1.16. okay, so this equation is just rearranged as like this, that is from this times, that is IA of S is taken outside, and we obtain an equation like that. Okay, and we are going to substitute the value for IA and EB here. Okay, because actually we have to obtain the transfer function of the armature control DC motor. So here we must obtain, that is the input is the applied armature voltage V A of S, and the output normally the output is a mechanical part, that is we are taking the output as the angular displacement theta. Okay, so that is we have to obtain theta of S by V A of S as our transfer function. Okay, so here, so in this equation, we are going to substitute instead of IA we are going to substitute this value. So in this value we know that theta of S is the, okay, and instead of this EB we are going to substitute this term. Okay, that is 1.19 equation. Here there also we obtain a value of theta of S. Okay, so this is the substitution part. So we have substituted the IA here. Okay, that is RA plus SL into, instead of IA of S we have substituted here, and instead of EB we have substituted KB into S into theta of S equal to VA of S. Okay, and by rearranging that, and also we are taking outside theta of S, we obtain an equation like that. Okay, and we must obtain, that is theta of S by V of S. So from this equation we obtain theta of S by V of S as this, that is KT by RA plus SL into J square plus BS plus KB KTS. Okay, and by using simple rearrangement in this equation we can make the equation using some terms, that is the electrical time constant and mechanical time constant. We can substitute that values here. So for that, that is just we are going to rearrange this equation. Okay, that is the previous one. So theta of s, b of s, and from the denominator part we are taking outside Ra from the first term, Ra, so that it becomes Ra into 1 plus SLA by Ra, that is SLA by Ra plus 1. Okay, and from the second term we are going to take outside Bs, so it becomes 1 plus J square by Bs, so here SS cancelled. Okay, plus KB KTS. Okay, and from this term we are going to take, that is Ra and B. Okay, Ra into B to the numerator side, that is KT by RAB. Okay, KT by RAB divided by, so here only S will be there. Okay, S into you can see a term 1 plus STA, that is TA is LA by RA, that is electrical time constant 1 plus STA into 1 plus STM, that is TM is J by B. Here S cancelled, so J by B is TM, so 1 plus S into TM. Okay, TM, that is mechanical time constant J by B, plus KB KTS becomes KB KT by RAB, because we are writing RA into B in the numerator part. Okay, so we have to write that RAB under this KB KTS. Okay, and we obtain that is KB KT by RAB. Okay, so the last equation theta of s by E of s as KT by RAB divided by S into, okay, S is taken outside. Okay, S is common for all, so S into 1 plus STA into 1 plus STM plus KB KT by RAB, where LA by RA is equal to TA, that is electrical time constant, and J by B is TM, that is mechanical time constant. So this is the transfer function of armature control DC motor. Okay. I hope all of you have understood well. Thank you.